This podcast is brought to you by LMU Munich.
Okay, thank you very much for the introduction. So yes, it's a great honor and pleasure to be here and to learn about the various aspects of the fascinating physics which is going on in this university and indeed in Munich more broadly. So today I would like to sort of summarize for you work over the last decade or a bit more, which, the way I would put it, has given us hope that finally we can actually get our hands around the problem of understanding the behavior of strongly interacting electrons in solids and molecules and other systems of interest. The most important thing to say is that this work has been done with a number of really outstanding collaborators, in particular Chris Marianetti, who is on the faculty of the Department of Applied Physics and Applied Mathematics at Columbia. A couple of postdocs, Hanghui Chen, who recently moved from Columbia to the Shanghai campus of New York University. Hyowon Park, who moved from Columbia to a joint position at Argonne National Laboratories and the University of Illinois at Chicago, and Jia Chen, who we're fortunate to still have at Columbia. Also, there's a bit of work by an absolutely outstanding graduate student, Chang Han, who is still with me at Columbia, and an absolutely outstanding postdoc, Ara Go. She has moved recently from Columbia to a group leader position at KAIST in Korea. And I'm not going to go over all the work in all these papers in detail, but this is some of the places from which material in this talk is drawn. I should also say that please ask questions at any time or make statements or comments if you want more information, less information, or anything. All right. The other thing I should say is that I have been fortunate enough to be involved with this entity called the Simons Foundation. One of the things that it does is it supports collaborations, larger groups of scientists who work together towards solving important problems. And in particular, I've been fortunate enough to get established and to direct the Simons collaboration on the many electron problem, whose PIs are shown here. And some of the things I'm going to tell you are really work that we have all done together, and I'll explain to you as the talk goes on why I think this is of particular importance. All right, but really these are the people who have made the substantive contributions to this subject. Okay, so the challenge, as you all know, properties of interesting materials are controlled by an interplay of the quantum mechanics of interacting electron systems and the specific structure of materials. This issue ranges from biochemical processes. This is essentially photosynthesis or light harvesting from the sun, where there is a complicated molecular structure whose job is to eat photons and convert it into excited electrons, which go somewhere where their energy is usable. Another example is materials. This is of vanadium dioxide, which, as you change the temperature, have a metal, essentially zero resistance on this scale, to insulator transition. A third example that I talked about at length yesterday is superconductivity. And all of these phenomena and many more, as I say, are electronic properties, properties that you cannot indeed understand on the basis of single electron quantum mechanics, but which are also specific in the sense that they depend on which material you're talking about. So one really needs to get one's hands on the interplay of these two features to understand what's going on. All right. So I think I'll just skip over this, except to say that superconductivity, as I discussed yesterday, is an interesting example of a many electron state. And natural questions to ask are which materials become superconducting and why. All right. So this I told you about yesterday. For those of you who weren't at the public lecture, I will just say that in general, the history of material science of interesting materials is characterized by serendipity, surprise, and reasoning by false analogy. Kamerlingh Onnes, who discovered superconductivity, wanted to see what happened to electron motion at very low temperatures, guided by the intuition that motion would stop. So he initiated a big effort in cooling materials, and he found not that motion stopped, but that it became perfect. You skip forward a large number of years later, 68 years from Kamerlingh-Hanna's discovery, 7 more years from Steglich's discovery, 22 more years from Steglich's discovery. We have at least 4 families of superconductors, all of different physical origin, apparently different physical properties. 4 superconducting families of materials. In each case, the discovery was accidental and based on measurements of naturally occurring compounds. Right? So you may ask, what other new superconductors are out there, and how high can we drive the superconducting transition temperatures of known families? So these are examples of the kind of questions that you would like to ask. And I think I will, just to summarize, here is a plot, which I also showed yesterday, of superconductors known as of 2012 and their transition temperatures, color-coded for different families. Here are 2 more examples discovered serendipitously. H2S, hydrogen sulfide, with probably under pressure, with probably the highest known transition temperature of a material, and monolayer of iron selenide on strontium titanate. Right? Each of these things, this was discovered by accident, this was discovered essentially by accident, this was discovered by accident. These 2 were the result of optimization of known properties. People essentially reasoned by analogy based on what we had, and using that analogous reasoning were led to these compounds. Right? This is a more interesting example. People, for reasons that are a little unclear, took a material whose transition temperature was 6 Kelvin, put it on top of a substrate, strontium titanate, and got very high transition temperatures, much higher than other members of the family. Right? So this is all to say that A, we have discovered families of materials. B, we can optimize their properties. And what this is saying is that it's time to go beyond what I was taught back in the Stone Ages was the paradigm of materials discovery. So this man is Kumar Patel. He was a director of research at Bell Laboratories when I was there as a summer student in 1983. And he gave a little lecture to us about the importance of materials in telecommunications and other aspects of society. And he summarized the process of materials discovery in the following way. He said it consists of 3 elements: heat, beat, and hope. And he said in 1983 that we can and must do better. And what I want to argue is that on the theory side, we're getting to the point where we can do better. Right? So the theory part of this program requires the calculation of energetics and dynamics of interacting electrons in chemically realistic environments. I would say that over the past 2 decades, we've had many successes, gained a lot of understanding, and still face some significant challenges. And in the rest of this talk, I basically want to outline those for you. But before that, I wanted to say that this field, the statement about challenges is something I don't make lightly. And the field of trying to say quantitative things about interacting electrons has had a bad reputation over sort of 50 years. You might summarize the situation in terms of these famous American cartoon characters. Right? This is the so-called Peanuts comic strip. And every fall, this guy wants to kick the American football. Or, if you like, solve a correlated electron problem. And every time, nature pulls some trick, and you wind up like that. Right? So as Charles Schultz didn't say in drawing this cartoon, this is a picture of Lev Landau, many people believe that fermion problems are numerically inaccessible and you just shouldn't bother. Right? So we're now positioned to do much better. I would like to start by showing you a couple of success stories. These are things that I've personally been involved in. They're just and not necessarily representative of the whole field. But I will talk about them because I know them well. All right? So here is a success story of limited scope, but still a success. So let's take two materials, lanthanum titanate, LiTiO3, and lanthanum nickelate, LaNiO3. In bulk, this material, lanthanum titanate, is a so-called Mott insulator. That means that if I use the conventional reasoning of electronic structure theory, essentially because it has one electron in the titanium D shell per unit cell, it should be a metal. It has a partially filled band. Right? In fact, it's an insulator. And the reason it's an insulator is electron correlations. Essentially, because of electron-electron interactions, electronic motion is jammed or blocked, and it can't conduct electricity. Right? Lanthanum nickelate, LaNiO3, is both experimentally and in conventional electronic structure theory simply a metal, right? With some modest enhancement of properties because of electron-electron interactions. All right. So Hanghui Chen, working with me, said that if we do something which is now possible in terms of material science, if I grow a superlattice of this material, alternating layers of lanthanum nickelate, shown here, and lanthanum titanate, shown here, and this is something that these experimental wizards can now do, then I should change the electronic structure in such a way that I go from having an insulating strip and a metallic strip to something which is completely insulating and which has had its electronic structure rearranged so that instead of being D7, lanthanum nickelate, this guy becomes, the nickel becomes D8 as in nickel oxide, and it becomes a correlated or Mott insulator. All right? So this is the cartoon. Basically, you transfer charge from this material to that material. Transferring the charge changes the electronic structure here, opening up a Mott gap. Right. So that was the idea. We did a variety of calculations which are shown in this unfortunately complicated picture. The main thing to focus on is this is lanthanum titanate, which is a Mott insulator with this gap. This is lanthanum nickelate. You can see the Fermi level here. At 0, it's a metal. There are states overlapping the Fermi level. This is Hanghui's superlattice with an energy gap at the Fermi surface and states near the chemical potential very similar to those in nickel oxide. So the prediction is that in the superlattice you get a small gap spin 1 Mott insulator out of these two components, a spin half Mott insulator and a metal. Right? So a year or so after Hanghui did that, the group of Jack Chakalian fabricated this structure. That's this picture. So they were able to grow essentially this. They observed it to be an insulator. This is when they grow under the same circumstances, just a film of lanthanum nickel oxide only. They get a metal. When they grow the superlattice, this is the same electrical resistance. They see an insulator, resistance increasing very rapidly as you lower the temperature. Similarly, they were able to see, and I don't want to take the time to walk you through this experiment in detail, but there's a high-energy spectroscopy that probes the local electronic configurations. And what they were able to see was that in our superlattice, the electronic structure was changed. So it's neither like lanthanum titanate, which is this, nor like lanthanum nickelate, which is this, but is instead this structure, which is essentially the same as nickel oxide. So in summary, they were able to verify that the charge transfer occurred, that the electronic structure was rearranged in the way that Hanghui had predicted. So this is not creating a new superconductor, never mind a new room temperature superconductor, but it is an example of how we can use modern techniques combined with modern ability to control the atomic and crystal structure of the material to generate something that has new properties. Right? And it actually works. Right? You can then go on and try to play, once you have this basic idea, then you can play games in various directions. For example, it is desirable for technological reasons to have a so-called multiferroic, a material which is ferroelectric, so that it's insulating and wants to have an off-center lattice distortion which produces internal electric fields, and is also magnetic. Right? And then you would like to have the magnetism and the electrical polarization talk to each other. Right? So it's very hard to find naturally occurring compounds that do this. Right? But Hanghui observed that you can do this using the same superlattice trick. He proposed one consider the material strontium-2 vanadium iron 06. So you start with strontium vanadate, which is a material which is a moderately correlated metal like lanthanum nickel oxide with the Fermi level here, and iron oxide, which is actually a Mott insulator with spins. Actually, this is in a low spin state. You then make the superlattice, you get the same level of charge transfer, and now what you have is two remarkable things. First, the iron becomes D5, right? And the vanadium becomes empty. Now, these things are interesting because to get a ferroelectric, what you want is an empty shell atom that is essentially not chemically bonded to its neighbors, so it's easy for it to move off of a central position. So the empty vanadium D shell will do that. And if the iron is D5, then the D shell is half filled and in a high spin state. And the half filled high spin D state is, for all practical purposes, like an empty state. The spin up half filled part is chemically inert. The spin down empty part is pushed up to a high energy by interaction so it doesn't hybridize. So this object is a multiferroic, and by playing games with lattice spacing and things like that, you can even control the insulating gap here. All right? So this is an example of just the optical conductivity you can calculate just to show you that it is an insulator. It does have a gap. The gap is lower in energy than another technologically important material, barium titanate, shown by dots. This is useful essentially because the solar energy spectrum is more nearly here than here. So this is a band gap which is in a useful area. All right? So this is a way, this kind of thing shows that at least for a certain class of properties, we're getting to the point of being able to predict structures that do things that we want them to do. All right. So here's another story. I said, because this is a talk originally formulated for the US and everything has to be great and huge, that it's a success story. I will explain what that means in a second. All right. But let me go back to these rare earth nickelate materials. I had mentioned to you lanthanum nickel oxide, LaNiO3. This is a moderately correlated metal. Every other material you make by putting something chemically similar to lanthanum here, yttrium, europium, neodymium, lutetium, all right, is actually an insulator. All right? It has a high temperature phase transition in which the bonds disproportionate. All right, that's shown here. There are 4 of these different materials. These are the nickel oxygen, this mean nickel oxygen bond from this octahedron or that octahedron. You see that above this temperature, which is probably hard to read but is sort of twice room temperature, the octahedra are the same. You go below this temperature and you have a short bond one and a long bond one, and this is quite generic. Now, this transition is a bit surprising, and there's a story here that I'm not really going to have time to tell you. The formal valence of this nickel is D7. All right, that means there's an odd number of electrons in the D shell, and in particular, let's say the T2G, XZ, YZ, XY orbitals are completely filled, and notionally there's 1 electron in the x squared minus y squared and 3z squared minus shared amongst the x squared minus y squared and 3z minus r squared orbitals. Now, in cubic symmetry, these 2 orbitals have a twofold degeneracy, and they have a shape. So the Jan Teller physics says that the system would like to lift this degeneracy, make a lattice distortion that either makes a short bond in the z direction if you pick this one, or a long bond in the z direction if you pick that one, and lifts the orbital degeneracy. So you pick one of these 2 things, you lower it, and you make a lattice distortion to match. That's the naive thing you would expect. In fact, what happens is you get the 2 orbitals are equally occupied, and you get this 2 sublattice disproportionation. Okay. Now, Ginyat Kaliulan, who was an incredibly creative person, argued that you could get away from this in a very interesting way by taking this material and breaking its rotational symmetry, changing its crystal structure from cubic to layered. So he proposed you have a structure which has 1 layer of this lanthanum nickel oxide, and then another layer of something else, let's say lanthanum aluminum oxide, which is just the wide gap insulator, that's here. So instead of each NiO2 unit having another NiO2 unit in all 6 directions, it only has an Ni2 unit in the plane, and it's different out of plane. So by constructing an appropriate material, you can break the symmetry. All right? He then argued that this symmetry can be used to control the orbital occupancy, so that if you break the symmetry, then instead of having these 2 guys equally occupied, you'll only have this one occupied. All right? And that's interesting because this statement of only having one of the 2 d orbitals occupied is the thing which is empirically crucial to getting high transition temperature superconductivity in the copper oxide materials. So what Colloquium proposed is that you make this superlattice, you completely lift the orbital degeneracy of the d orbitals, and you get something whose electronic structure should be favorable to have high Tc superconductivity. Right? So that's the proposal. All right? And it's part of this same general question, can you control the electronic properties by materials design? All right, so we looked at this in various ways, and what we've discovered is that the physics is in general different from what they proposed. We can talk about strain and symmetry breaking and get various results. All right, now, this question has been experimentally investigated over the years. Probably the definitive result is from Eva Benkaiser and collaborators at the Max Planck Institute in Stuttgart. They used a variety of extraordinarily clever high-energy spectroscopies to investigate this material, where instead of just one layer, you have 4 layers of lanthanum nickel oxide then with these spacers, so it still breaks the symmetry. And they investigated the orbital polarization, the degree to which one orbital is occupied and the other orbital is empty. Right? And they did this as a function of the composition of this material, which implies a strain in the plane. Right? And these are their experimental results. Right? You can ask what is the polarization in this layer or in this layer, and you can discuss it as a function of strain. And they got various answers. Right? The main thing you take away from this is that the orbital polarizations are all small. 5%, 10%, 20%. You cannot get to the complete polarization that Colloquium wanted empirically. All right. Now, you can apply the various many-body methods that I'm going to tell you about a bit later, all right, and calculate this same thing. So this was done by Hyo-won Park and Chris Marianetti, and recently published. I apologize for this somewhat busy figure, but the main thing I want you to take away is here are the experimental data, the black dots and this line. Here are the calculations, are many interacting electron calculations with essentially no fudging, we just did it. Right? And what you see, and this, for those who are aficionados, these red things are just non-interacting electron band theory. What you see is that there's an offset between theory and experiment, but the strain dependence, the basic splitting between the two different inequivalent, and the basic splitting between the two inequivalent nickel layers is in quite good correspondence with the experiment. Right? So again, I would argue that this is a success in that materials theory works. Right? We are able to calculate something which is essentially what's found in experiment and where many body effects are important. It's not a success in that this turns out simply not to be a good route to getting a new kind of high temperature superconductor. All right, so the summary of this introductory portion of the talk is that I've given you a couple of examples where I hope you will agree that we have at least some degree of control over this interplay between interacting electron physics and crystal structure. Right? And so with this degree of control, we can understand a range of experiments and control some properties. All right. Now, in the rest of this talk, what I want to do is give you a look, as it were, under the hood of these calculations and explain what is really the theoretical status of this kind of calculation, to explain what it is that we can do, where the difficulties are, where the successes are, and what are the open problems. All right, so first statement. Why is this a hard problem? I showed this yesterday also. It's a quote that I love. Dirac, in 1929, told us how to solve interacting electron quantum mechanics. He wrote down the many-particle Schrödinger equation. He explicated its logical structure and told us basically what to do about it. And in this paper, he wrote, the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are known. The difficulty lies only in the fact that these laws lead to equations too complex to be solved. And then he went on to say, it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed. Right? So why has it taken us almost 100 years from when Dirac wrote this to get to the point of having approximate practical means of applying quantum mechanics to the many electron problems? All right? So the basic idea is that quantum mechanics involves a wave function. The wave function has coordinates, and if you have a lot of particles, it has a lot of coordinates. right? So the difficulty of just writing down all possible wave functions grows exponentially in the number of particles. That's one problem. The worst problem is that the particle coordinates are entangled. For example, because these guys are fermions, if I interchange any two of these coordinates, this wave function has to change sign. So preserving that entanglement correctly creates ferocious difficulties, and in fact it's believed that a direct, I don't know why it wrote direction there, a direct solution of the many fermion problem is in the class of things which can't be solved in polynomial time, or if they could, then everything else could be. Okay, so now I want to discuss that in a little more detail, all right? So entanglement is a word you've heard of. Here is a simple example. Quantum mechanics plus Fermi statistics, which imply anti-symmetry, implies that the bits of a wave function are correlated. So if I take two electrons, let's say in a given spatial quantum state, the wave function has to be a singlet. It has to be anti-symmetric under interchange of the two particle spins. So it has to be proportional to this combination. All right? And in principle, these correlations persist to arbitrarily large distances and among all possible pairs of particles. So apart from the fact that the downspin got lost here, if I take these two guys and separate them over an arbitrarily large distance, what I will see is that this minus and this entanglement will still persist. And the real conceptual difficulty, which it took us a long time to get over, was that the formulation of quantum mechanics, which Dirac gave us, was essentially built on wave functions which preserve this entanglement property over infinitely separated particles. Right? And what you really want to do to make progress is to localize the entanglement. All right? Now there's an additional difficulty, all right, which is that one talks about entanglement in simple models like this. If you want to start talking about real materials, there are extra issues just from all of the realistic factors, which lead to an extra power law burden on your computation. Now, as a computer scientist, you would say power laws are unimportant. The only question you need to ask about is the basic scaling exponential or not exponential. However, the power laws are large in real materials and come with very large prefactors. Here's a very simple example that people are interested in studying for various technical reasons. You can take a metal which is copper, you can take one cobalt atom and stick it on the surface. That's shown here, right? So then this cobalt atom has a d shell. It has electron-electron interactions. This d shell holds a spin, and you want to know how the spin here interacts with the copper stuff in the substrate, right? So if you actually write down the realistic interaction Hamiltonian for a cobalt atom on the place where it actually sits on the surface, which has relatively low symmetry, you have a bunch of interaction matrix elements just within the cobalt d shell, which are described by 129 different interaction parameters. Right? So if you just have one atom in one place, you get 129 parameters. That kind of thing, the complications associated with that kind of thing grow rapidly when you try to describe any kind of real situation. Right? So you have a large power law overhead of, let's just say, realistic stuff around your calculation. Right? So these are the two essential difficulties. So what does one do about this? Well, there are two approaches. The first is to focus on simple model systems, which, because they're still quantum mechanical, contain the exponential barrier and the entanglement physics, but don't have the overhead. Or you can try to make realistic theories which treat all the real materials overhead and tend to compromise on the many electron quantum mechanics. Right? So here's the model system that everybody favors, the Hubbard model. It's probably the simplest thing you could write down. It's a lattice of sites. Each site has one orbital. It can hold 0, 1, or 2 electrons. And then there's an interaction which lives only on the site and favors or disfavors double occupancy. So this is the simplest, in some sense, theoretical model of interacting electrons you can write down. Right? It still has the exponential hardness and entanglement properties, but as a gross caricature of real materials. All right? In the area of realistic methods, the workhorse for many, many years has been density functional theory, which comes from a theorem of Hohenberg and Kohn and was made useful by Kohn and Sham the next year. And what this does, and this is characteristic of all the realistic methods I know, is that it makes a compromise. What it says is we're going to get limited information, in the case of density functional theory, the electron density and the ground state energy, by solving not the full problem, but an auxiliary problem which is simpler, all right, and tractable. Right? For density functional theory, the auxiliary problem is of non-interacting electrons in a self-consistently determined potential. So you solve a single particle Schrodinger equation in this potential, which is the moving part of the theory, and you make this from this you infer a density, and then you make the density consistent with this potential. Right? Now, as it turns out, we don't know what this is exactly, but we have many reasonably good approximations. So this works in many circumstances. However, there are lots of things that you might want to know which are not contained in the restricted class of information that you can get out of this. One is the excitation, or not correctly contained. One is the excitation spectrum. Here's lanthanum titanate, the material I showed you before. And density functional theory gives you a completely wrong prediction, for example, for the photoemission spectrum. Another example is superconductivity. These density functional theories won't tell you why this guy has a 100 Kelvin superconducting transition temperature and this guy has a 6 Kelvin superconducting transition temperature. All right? So to go beyond this, what you might wish to do is correct density functional theory. All right, so that's just a brief sketch of methods. All right. Now, let's say of approaches. Now, once you have approaches, then you need to discuss the theoretical methods that you might actually use to solve these problems. All right. And there are two really. One is a direct attack. You can essentially solve the full quantum mechanics problem as well as you can. The two major approaches are Monte Carlo, and I'll describe that in a second, and properties that exploit, let's say, special properties of the ground state, which I don't really have the temerity to talk about here in front of an audience of world experts, but density matrix renormalization group, matrix product states, and related things. Right? Then the alternative method is what I would call an indirect attack. You can generalize the basic concept of density functional theory to the idea that you will solve an auxiliary problem which is simpler, and from that auxiliary problem get some restricted class of information that is useful. All right. So I would like to give you just a couple of simple examples. One which I consider to be particularly cute is so-called diagrammatic Monte Carlo. Right? You all know that you can express the physics of interacting particle quantum mechanics in terms of Feynman diagrams. The way you generate this is you take your Hamiltonian, you partition it into two parts, you make an interaction representation with respect to one part, and you formally expand in the interaction part. This gives you a series which you can represent as Feynman diagrams. Right? And the idea of diagrammatic Monte Carlo is now you just sample that series stochastically, both the positions of the operator insertions and their times, and the nature of the operators that you insert. So if you like, you can think of a Feynman diagram series for any quantity as the grand partition function for a gas of pseudoparticles. The particle is the vertex of the Feynman diagram. The interactions between particles are the propagators. And what you're doing is just using a Monte Carlo to evaluate, and the interaction constants are the bare fugacities. So what you're doing is just simulating the grand partition function of the pseudoparticles, which are the interaction vertices, by sampling this series stochastically. So this idea has been around for a long time. It was introduced in a version which really showed its effectiveness for some class of problems by Alexei Rubtsov, and then picked up by Philip Werner, myself, Sasha Lichtenstein, and others, and then Nikolai Prokofiev and Boris Vistanov. Right? So this is the idea as I showed you. The diagram series is just a grand partition function for the gas of vertices. You add shift or remove shift positions of vertices. This idea sounds a little bit hokey, and indeed I got interested in it originally because I thought that even though it wasn't a good method, there was a class of problems for which it would be the only method. Right? It turns out to be incredibly powerful, and the simple reason is that it's like an adaptive grid for quantum many-body physics. When you do this, what it does is it puts the vertices where you need them to control the energy. So here is a time dependence of some random physical quantity. And the basic idea is that all the energy comes from the initial rapid drop in time, or here imaginary time. The physical properties that you care about are controlled by long times here, where the variation is slow. So you would like to have a method which doesn't just uniformly discretize the time axis, but puts more points here where the variation is rapid and you want to get the energy right, and fewer points here where you don't need them. Right? And that's really what this method does. Right? Now, a loose way to say this is that everything to do with quantum mechanics is manipulation of matrices. The cost of doing anything with a matrix, if you do fast updates, is the cube of the matrix size. And these adaptive grid things let you get matrices which are 100 times smaller than the matrices that you would get with other methods. And that means that you win by factors of order 1,000,000. Right? And that opens doors that were previously closed and lets you calculate lots of things that you couldn't do before. All right. Here's a second thing, the approach of special properties of ground states. All right. I talked about extended entanglement. It's now known in certain simple cases and believed in a much wider variety of cases that ground states, and by extension the low energy states that you really care about, are special from the point of view of entanglement. Unlike a generic state in the Hilbert space, ground states are believed to have spatially localized entanglement in a way that I don't have time to make precise for you. So the subspace of all of Hilbert space that contains these wave functions with localized entanglement is much, much smaller than the full size of the Hilbert space. And therefore, essentially, you can construct your ground state by making wave functions which only have localized entanglement, and therefore you can construct your ground state out of an enormously smaller set of states than you would need to describe the full Hilbert space. This is the basic idea behind a variety of related methods: density matrix, renormalization group matrix product, tensor network methods. And all of these things, because they work explicitly in a low entanglement, or I should have said localized entanglement subspace, all right, are much smaller problems computationally, and in many cases are believed to be power law algorithms, although sometimes the power can be high. All right. The third example that I wanted to sketch for you is these embedding theories, for example, dynamical mean field theory. And just to explain this, let me give you some notation. The basic object in many-body physics is an electron Green's function. So if I choose some basis of states for my many-body for my single-particle Hilbert space, the Green's function is a big matrix in this space. It's a function of frequency. There's a term which is the single-particle part of the Hamiltonian, and there's a term which encodes the interaction. All right? So to fully describe the physics, I need this matrix in amongst all of the single-particle states of the system. Right? That's essentially impossible to get. Right? So what dynamical mean field theory does, in effect, is parameterize this big matrix as a sum of a much smaller number of things. Instead of essentially an infinite number, it parameterizes it by a number which could be as small as one of these things. And then there's some rule that I don't want to tell you about for taking these things and putting them together to get an approximation to the physical self-energy. The choice of this, there are various flavors which are controlled by this choice of parameterization function which aren't interesting. The thing which is interesting is that this, because it's a system of far fewer degrees of freedom, is the solution of a much simpler model, which again you can solve. So for example, one thing you might do is approximate your full self-energy, a function of momentum and position, by saying I'll take momentum space and I'll divide it into some number of patches: 1 patch, 2 patch, 4 patch, 8 patch, 16 patch. And I'll just assume that my self-energy is piecewise constant. So it takes one value in this patch, one value in this patch, and so on. Right? So that's one of several examples of how to do this. Then if you want to, here you need to compute only 16 things instead of a continuous function. And the problem of finding these 16 things is simple, relatively speaking. Right? And that gives you an approximation to this guy, which can become better and better as you increase the number of patches. All right? So we can now, and by we I really mean Emmanuel Gull, can now carry this out to a quite high level of sophistication. For high temperatures, you can get to number of patches up to 100. You can see how things like the energy converge with respect to system size. In some areas, you can compare it to other things that are known. You can see that these methods can carry you to much lower temperatures. So basically, we know that this thing works and it converges to the right answer. Okay, so that was a very qualitative sketch of a wide variety of methods that are now available to us. each one has a certain level of approximation, makes a compromise in a certain place, and gets answers whose reliability you would like to assess. Right? So one of the very important things that this Simons collaboration has done is bring together all of, perhaps not all, but most of the practitioners of most of the different methods and gotten them to work together to systematically compare their results. Right? So by now we have studied, for example, the two-dimensional Hubbard model in this paper by a wide variety of methods listed here, ranging from diagrammatic Monte Carlo defined in the continuum, dynamical mean field theory, fixed node Monte Carlo, a different embedding theory, DMET, auxiliary field quantum Monte Carlo, density matrix, renormalization group, quantum chemistry methods. All right, we can calculate the ground state energy, we can calculate thermodynamics, we can calculate phase diagrams, and for moderate couplings in the Hubbard model, we can now document which methods work and which methods don't. And there's enough consistency between the methods that work that I think it's fair to say that we have within our hands a complete and controlled solution to the basic properties of the two-dimensional Hubbard model. Right?
So
Yeah.
Sense complete. I mean, maybe about the ground state properties.
Okay. Correct. So the thing which is documented in this paper is the ground state property and the phase diagrams. All right? And even here, and I'll come back to this, I would say that we have in prospect a complete solution. I would say that we have a complete solution for ground state properties and a reasonably complete solution for excitations for U's up to 5, I would say now. For stronger coupling, we're still working. But I think the solution is in sight. Now, you said excitations. Here's an example. Right? From the same paper. So we have this at a relatively high temperature. This is the real part of the self-energy at a particular Matsubara frequency from dynamical mean field theory, from a dual fermion theory, from direct diagrammatic Monte Carlo. These things agree.
You still like them on the real axis?
Yeah, sure, but that's a small step. That's analytical continuation.
But that's not a controlled state.
I would.
Continuation has its problems.
Mm-hmm. No, that's quite true. But there's, first of all, I'm not going to have time to say this, but there are a complementary set of things which let us study this directly on the real axis, right? So that provides some comparison and control over analytical continuation, right? And then there's a separate talk that we should just talk about offline about other analytical continuation methods. I think it's more controlled than you would. I mean, I would agree that as it's generally implemented, it's not a controlled method. But I think that there are more controlled methods than people generally appreciate. Right. But look, this is not to say that the problem is fully solved yet. But this is to say that we now, for the first time, for some properties and in some domains, have agreement for physical properties extrapolated to the thermodynamic limit of the Hubbard model with error bars. So basically, we know what we're doing. Right? So that's why I think that a solution to this model is in prospect, and parts of it we have. Right. I said that this basically works for modest U. This is U equals 4 and a doping of 0.8, for example. There is progress at larger U. Recent beautiful work by Steve White, Shiwei Zhang, Philippe Corbeau, Garnet Chan, using, again, quite different methods, has now, for example, sorted out what is the ground state at this particularly challenging point of 1/8 doping and large U. They have found that the ground state is vertical stripes. It's not superconducting. They know how the energy changes as you change the stripe wavelength. They know how the superconductivity turns on. And again, the key point of this is that you see there are different colors and shaped symbols here. These are 3 or 4 completely different methods, which are now getting the same answer. Right? And to my mind, that's really the test that one knows what one is doing. All right. So just as a bit of shameless self-advertisement, these are agreement to within a few percent. All right. If you now go back to this particular approximate theory, which I showed you in 1 or 2 slides for some properties where you can compare it actually works, then I now want to present to you some of the results that are obtained from this. Did you have a question? Or were you? Yeah.
So if you say stripe
Yeah.
Do you see signaling susceptibilities in DCA?
Wait, no. DCA, the momentum resolution is too coarse to see stripes. The things which are here are Garnett-Chan's DMET, which you can go to much bigger systems and see. But is not in a position to see stripes to date. Again, there are various extensions that you can discuss that we can talk about offline that probably will become in a position to, that need to be first implemented and then benchmarked. But the method as it stands now is not in a position to do that.
I'm not talking about symmetry breaking, just the susceptibility.
Yeah, I know, but even that, I mean, again, if you're coarse graining momentum space like this, you just don't have the resolution. As I say, there are extensions which will start to let you get your hands on that. They're presently being implemented. They're not yet benchmarked, so we don't know. That's an area where I would say there is hope, but not yet substance. All right. So you can do this. You can calculate things, right? And you can get results which are both in agreement with these other theoretical methods where you can compare them, all right, and quite consistent with experiment. And in particular, you can find out that I think now, essentially without any doubt, that in the absence of stripe phases at particular commensurabilities, the Hubbard model does have a D-wave superconducting ground state over a reasonable range of its phase diagram. All right? You can calculate the phase diagram over a range of U's. You can compute properties. You can compute physical properties. You can compare them to experiment. This is one of my favorites. It's Raman scattering. And what you see as you go from so-called overdoped to underdoped is a change from normal state to superconducting state, where you get a big peak in the Raman scattering spectrum in the superconducting state, that's here, to underdoped, where you see a suppression with temperature in the normal state and a weak peak at much higher frequencies in the superconducting state, that's this. All right? You can ask within this class of theories how you optimize the transition temperature. You can analyze the origin of the pairing. I don't want to go into this in detail. So what this says is that for this simple two-dimensional Hubbard model, I claim that the solution is within reach. We know that the ground state has a superconducting phase. We know how to characterize the properties of the superconducting state. We know how to get the same answer for ground state energies and basic correlation functions with different methods. We know in some cases how to find stripes. So I think that the prospects for getting to a complete solution of the Hubbard model are very good. Right? So to put this poetically, Antoine Georges, my friend and colleague, said that the Hubbard model is one of the peaks of theoretical physics, and I would like to argue that we're getting close to the summit of this peak. All right? So now I'd like to turn to real materials. This is another clever thing that Antoine did. This is a painting which you can find in the Kunstmuseum of Basel by Henri Rousseau, which is titled "A Physicist Challenged by a High-TC Superconductor." All right? So the question, the issue which is nicely expressed by this is how do we take our insights from simple models and navigate through the jungle, as you might call it, of real materials? All right? So again, this jungle is too complicated to deal with directly in most cases. So what we do is, in one way or another, take all the degrees of freedom, partition them into a correlated subspace and a background. Typically, you can define the correlated subspace by picking out orbitals that you like. There are technical ways to do this that go by the name of maximally localized Bonnier functions or projection methods. Right? You treat the correlated subspace by some kind of many-body method. You treat the background by a cheap method, and you do some kind of self-consistent embedding. Right? So an example of this self-consistent theory is density functional theory, and I'd like to just give you a little bit of formalism. From a formal point of view, you can express density functional theory as a functional of the electron charge density, rho, and its conjugate potential, which I've written here as V. And this potential has two parts. One part which is just the electron free energy in this potential. Three parts. One part which is the functional, which tells you of the density, which tells you how to get this. And the third thing is a Lagrange multiplier. So if you demand that this functional is stationary with respect to variations of these two things, you get two equations. Stationarity with respect to the potential says that the density has to be self-consistent. Stationarity with respect to the density says that the potential, which is the functional derivative of this guy, has to be the one which is right for this density. Right? So if you knew exactly what this functional was and how to take the functional derivative, then you would have an exact theory for the density. We don't know this. You need an approximation to this, and that's all the different density functionals that you see. Right? Now, this has been very successful, but it has a number of limitations. This is a simple and instructive example I want to show you based on work that Jia Chen did. This is a complicated molecule. It has an iron atom surrounded by stuff. All right? Now, it turns out that this iron atom can be in two states. A high temperature state where there's a magnetic moment. You see that here. This is temperature times the magnetic susceptibility. The fact that this is constant up here says that the iron has a free spin. Then at some temperature, boom, it goes to something which has no spin. So there's a high spin to low spin transition. You can ask what are the high and low spin states. You can get them in density functional theory, and density functional theory grossly overestimates the energy difference. This is an energy in EV scales. You have a low spin state, you have a high spin state. They differ by 0.6 EV. That's way too big to get a transition here. Right? Here's another example, these Nicolate things. Density functional theory doesn't predict that this structural transition, which I alluded to before, occurs. All right? And it predicts actually metallic behavior for everybody. All right? So you can do this same thing and extend density functional theory by a many-body method, here dynamical mean field theory. It's exactly the same logic, except now you take your density functional theory and you supplement it by information about the many-body physics in the correlated orbitals you've distinguished. So instead of having two variables, you have four, but you have the same story, that you have a functional. It should be stationary with respect to these things. And then what you get out is the self-energy, which gives you correlations amongst the special sites, the density, and so on. Right? So again, it's formally exact. As in DFT, you need approximations in two places. One is to get the exchange correlation potential from the charge, and the other is to get to solve the many-body problem in the correlated subspace. Right? So what people do in practice is you take this general functional and you assume that it's the sum of two things, one, the density functional that we know and love, and one, a many-body theory that we can solve. And then you have to make a so-called double counting correction, which I'll come back to, which accounts for the fact that this is really one functional and you can't split it into two. Right? So, we've done this, we've implemented it. The procedure is basically you start with just density functional theory, you get some orbitals. These orbitals define a dynamical mean field theory problem in the correlated subspace. You solve that, you recompute the full charge density. From that charge density, you resolve your density functional equations, and you do this whole thing until it converges. For professionals, it's essential to do full charge self-consistency. Right? So we can do this, all right, and we can get information. So this is what I showed you before. You have this spin crossover molecule. All right? This is the density functional theory I showed you before. If you do DFT plus DMFT, well, if you do DFT plus U, which is the Hartree approximation to this theory, in fact, you go from having the energy 0.6 eV, which is way too big this way, to having the energy almost 0.6 eV big in the wrong direction. You include the quantum many-body theory, and now the two states have approximately the same energy. All right? So this combination of band theory and many-body theory is doing something useful for you. All right? Now it's interesting to look at what's really happening. All right? If I look at the two states, the high spin state, where we get essentially the same answer as DFT plus U, and the low spin state, all right, what you see here is essentially the density matrix projected onto the iron site. In the high spin state, what you see is that the iron just has a half-filled D shell. It's electrically inert. In chemistry language, it's single reference. Density functional plus U is okay. In the low spin state, you have a rather different occupancy. And in particular, you have two of the states which are partially occupied, but affected by correlation physics. So it's this thing which dynamical mean field theory is doing for you that the other methods don't. It's capturing correctly the energetics of valence fluctuations in this correlated environment. Right? You also can talk about charge self-consistency, which is important. Now, so this is what's good. Here's what's bad. Right? When we solve this impurity problem, this DMFT problem, we have to choose an interaction on the correlated site. There are various ways to choose it, but you may ask, how does the answer you get depend on the value of the interaction and the double counting you choose? All right, and what you find is that the critical value of the energy difference between the high spin and low spin state, just focus on these. These lines have to do with density functional theories, which are just terrible. Focus on this. What you see is that the answer you get depends very sensitively on the Hund's coupling you choose. What you see here, even worse, is that the answer you get depends very sensitively on the double counting contribution that you choose. All right? This Hund's coupling is something that you can imagine determining, and in fact, this is about the right value, as we know from by other reasons. The double counting is something for which there is not yet a good theory, and the energy difference depends sensitively upon it. So to summarize, what we learned from this spin crossover molecule is that a many-body treatment is crucial for the energetics of hybridization in a correlated environment, that charge self-consistency is crucial, and that the key source of error is the uncertainty in the beyond DFT interactions, and in particular in the double counting correction. These are bigger uncertainties than the ones in the solution to the many-body problem. All right. So you can play this same game with the rare earth nickelates. Because I'm running out of time, I'll just skip lightly over it and say that, again, we can apply this method. We can get much better agreement with experiment and standard methods for things like the pressure dependence of the metal insulator transition. We can account for the photoemission spectrum. But in all these calculations, we had to use empirical input. In particular, by comparison to high energy, we used comparison to high energy photoemission experiments to determine the double counting correction and the Hund's coupling. All right? So to summarize, this theory is, I believe, a successful but semi-phenomenological treatment of correlation physics in a realistic environment. And the places where we need theory and where we need to do better are the double counting correction, that is, understanding exactly how we embed the interactions of this correlated problem into the background theory, and how to treat other non-local interactions. All right, so to start to get our hands around this, I'll just say in the last 2 minutes something else we've been doing very recently. We've taken sort of the simplest possible realistic theory, in this case a chain of hydrogen atoms. All right? So in this problem, all right, we treat the full E squared over R Coulomb interaction with all the matrix elements. And you can either do what chemists call STO6G, which means you just take one orbital per each hydrogen atom, or you can just do the full basis, essentially treat the problem in the continuum. All right? We can again ask, how well do all of our different theoretical methods shown here do in computing the ground state energy? And we haven't yet gotten to excitations. That's in the next step. Right, as a function of interhydrogen separation. So doing this forces us to come to grips with two of the key issues of real materials. First, the full matrix elements of the Coulomb interaction, and second, the realistic structure of the realistic full basis that you need to deal with problems in the continuum limit. And what you find after a certain amount of optimization is that, again, there are a wide variety of methods which now all get essentially the same answer to within a milli-Hartree. That's these numbers. All right? So I think that this is very encouraging, and I would like to conclude that a new era for the materials theory of these quantum materials is starting, and that we're beginning to be able to, let's say, tame the jungle of real materials and electron-electron interactions. So with that, I will thank you for your attention and stop. Yeah.
Is there a physical way to understand? So, I mean, if I understand correctly, most of these high TC superconductors are not really 2D, they're quasi 2D, so there's some role played by third dimension.
Yeah.
Whereas the 2D Hubble model is really exactly 2D. So is there a physical way to understand how the third dimension is kind of incorporated in this 2D surface?
Well, no, I don't think there is, because it isn't. I think that the right way to say this is that I think it's more or less an established fact now that the 2D Hubbard model contains the essential physics of the materials, namely a dx squared minus y squared superconducting state, a pseudo gap, a striped state, and so on. All right. So I think that the weak coupling, which undoubtedly exists in the third dimension, is not of primary importance. That said, it's obviously there. It will obviously have some effect. And it's an obvious next step in the theoretical development to ask, can you get your hands on it? Now, on the empirical side, there's a wide variety of these high TC compounds which have a wide variety of strengths of the interplane coupling. And the properties of all the different materials are in broad terms, the same. So I think that the empirical evidence is that the coupling in the third dimension is not of crucial importance. But again, it will have an effect, and we don't yet really know what it is. But it's certainly not included in the 2D Hubbard model, which is just 2D.
Okay, I'd like to get your opinion on my question, which perhaps goes beyond the scope of your talk, about alternative methods. In particular, during the recent 5-6 years, people from a different community, maybe from particle physics or gravitational community, use the ADS CFT correspondence to attack strongly coupled systems, in particular also high TC superconductors. So if possible, can you comment on that?
Yes. Sorry, there are too many slides, and I probably should have just... Yes. All right. So basically, the ADS-CFT thing is an example of a use of effective field theories, right? And the way I would say it is that there's really two complementary things. And indeed, it's a problem that was mentioned on one of my slides, but I didn't specifically mention. These are two complementary approaches. In my view, effective field theories, for example, this ADS-CFT, things that come out of this ADS-CFT correspondence, are very good ways to, let's say, parameterize and describe the low-energy physics of different situations. Right? So there are ways to let you determine what are the generic properties that follow from symmetry, whether obvious symmetry or some kind of hidden quantum symmetry, and characterize then the long wavelength physics, what are the collective modes and other properties. Right? They are, to my knowledge, entirely useless in answering the question of why does YBA2CU307 have a 90-degree TC and LA 1.8 SR.2 CuO4 have a 40-degree TC? Or why does this copper oxide thing superconducting to begin with and analogous compound like lanthanum nickelate not superconducting? So there's a sort of complementarity between effective field theories and these sort of numerics. And one of the things which is missing from the numeric side of the field is a good and systematic way to connect to effective field theories. Right. So that I think is the generic statement. Now, as far as I know, the ADS-CFT correspondence has essentially successfully found a gravity dual of a superconducting phase, for example. But I don't think it's really yet told us anything new about superconductivity that we didn't know already. But it's quite likely that it will. I mean, in particular, there are intriguing issues of the extent to which you can encode quantum critical points into this theory and then see how they play with superconductivity.
Further questions, particularly from the students. Don't be shy. You must also ask questions.
Sorry.
Yeah.
At least in the normal superconductors, if I remember correctly, the let's say the typical distance between Cooper pairs is much bigger than typical lattice spacing, right? So to form a Cooper pair, let's say you need a certain distance, a certain size of the system at least. For numerical simulations, what size are these, and are they contained in them, or are they because of some other reason, so it doesn't even matter?
That's an interesting question which needs to be unpacked on several levels. The question is the size of the Cooper pair versus the size of your, let's say, computational box. So, in fact, the methods that I alluded to towards the end of the talk are formulated in momentum space. So they don't have a size, all right? They have relatively coarse resolution in momentum space. So it's difficult to get them without additional assumptions to tell you things like what is the coherence length. You have to use indirect arguments, let's say. But they don't have a computational box, right? But the second thing is that there is a whole interesting field, which I'm not going to comment on here, of, let's say, mesoscopic superconductivity. And in fact, you can have still superconducting properties, particularly for conventional superconductors, even in, let's say, quantum dots which get to be comparable to the size of a coherence length or smaller. You can make very small dots of lead which still have superconducting properties. Right? The key thing you need is that the boundary of your dot isn't pair breaking, that it doesn't rip apart the Cooper pairs. Right? And you need to have, roughly speaking, many electrons comprised within one Cooper pair radius. But you can shrink the thing somewhat smaller than a coherence length and still get superconducting properties. And where the interesting physics happens is that as you make it smaller, the number phase uncertainty relation becomes more important. Or to put it slightly differently, the charging energy of these small grains becomes important. So you start to see stronger quantum and other fluctuations of the superconducting phase. And studying exactly what those things do is a very interesting area of physics.
Just one question. Okay, go ahead. For, let's say, a more complicated question about the Fermi-Hubbard model in 2D, like the entropy per particle at the phase transition of the D wave. How long do you think is it going to take until we can answer these questions, or can you already give something in this direction?
All right. So you put your finger on one of the big weaknesses of these theoretical techniques, all right? And that is that while we can calculate the temperature dependence of the energy, all right, getting the entropy, we can't get the entropy directly, or the free energy directly. So to get the entropy, what you have to do is start from a known configuration and compute the energy very accurately as a function of t, and then take internal energy and take the derivative, all right? And that's more work than basically we've been prepared to do to pin things down to pin down exactly what's happening at the transition, or even at higher temperatures where there are interesting questions of making connections to cold atoms, right? But it's essentially a matter of laziness. To get entropies, you have to compute energies accurately enough that you can take a reasonable derivative. And this also relates, actually, not having free energies to forces at higher temperatures are a bit awkward, because if you want to understand lattice deformations, you want forces, which means you want to take gradients of the free energy with respect to atomic positions, right? And we don't have the free energy, we have the energy, the internal energy. So that's a weakness. So we can do it indirectly. I mean, we can track the temperature dependence of the order parameter, we can look at the change in internal energy, and then you can back out the specific heat if you want to assume the transition is mean field-like, and thus get entropy jumps and things like that. But it hasn't really been done yet.
The question at the first of the slide, you said that in nighttime systems you have electron correlation. Can you say a bit more about this?
Yeah, and I should say that this is also a interesting, somewhat controversial issue. There's two separate things. One is the importance of quantum coherence over long times and distances. And I'm not a professional in that field. What I know is that there have been a number of claims, and these have been disputed by a number of other people. And it's not obvious at this stage how important quantum coherence is. All right? But it's certainly true that you absorb a photon, it makes a particle-hole pair, and in general this cascades in energy down to several particle-hole pairs, which then do something as they propagate and go through the light harvesting molecule. So the right way to say it is that there is more than one particle-hole pair, and in an environment with a bunch of other electrons. So that's the sense in which there's a correlation problem. I suspect it's a few electron correlation problem rather than a many electron problem, and that ultimately it's closer to a classical problem. But it's, another way to say it is it gets you into this field of multiple exciton generation.